Today we are going to discuss about the transistor under the electronic devices and circuits. So first we will see the background of this one, the history part of the transistor. The transistor has replaced the conventional tube. Earlier the tube was in this form. This was the anode and this is your cathode. This electrode was known as grid. So earlier this 3 electrode device, it was known as the triode. Now this was having some of the drawbacks earlier. The drawbacks of the triode valve. This was conventional tube. So we can first see what were the drawbacks of the tube. Then we will come to the transistor part, because transistor is the semiconductor device. So what were the drawbacks of the triode valve? Then the transistor has overcome those drawbacks up to the some extent. So let us see first then what is the drawback. The drawbacks of the triode valve were the transit time, then second was your inter-electrode capacitance, large size, high power consumption, basically these were the drawbacks of the triode valve when we were using these tubes on the, especially these drawbacks were coming when we were using the triode valve on the high frequency. The first one, especially the transit time, was the drawback on higher frequency when the triode was being used for the higher frequency. So then inter-electrode capacitance, as you can see here, that this was the glass tube and it was having a cylindrical shape. So in the cylindrical shape, the size of this one was slightly larger. You can say it was about 4 to 5 inch. And then these inter-electrodes means there was a lot of gap between anode and grid, and grid to cathode and cathode to anode. So we were having a lot of gap in this one. So on the higher frequencies, what was the problem here, that your anode to grid capacitance was being formed, then from grid to cathode capacitance was being formed. Similarly from anode to cathode also the capacitance was being formed. So because of the inter-electrode capacitance, and this capacitance was the imaginary capacitance because of the high frequency in use. So due to this one, if we consider the case of grid to cathode capacitance, then input, whatever input was being to be amplified, so the applied input from here, you can see, if we apply the input between this terminal and this terminal, then some of the power was getting sorted to the ground because of the imaginary capacitance formed between grid and cathode. Then from anode to cathode also there was a capacitance formed here. It was known as capacitance from anode to grid. You can write C, A, G. This was your C, G, K, and then again here, from here also the capacitance was formed imaginary. This was your C A K. So as on the higher frequencies, the capacitive reactance of these capacitors formed was going down, because as you know, the Xc is equal to 1 upon omega C. So as the frequency is going higher and higher, your Xc, capacitive reactance of all the capacitors, is going down. That's why the input was getting dropped down to the ground. This electrode is to be grounded. Then same way the feedback was coming from the output to the grid, and similarly output was also getting sorted through this capacitance. Hence the performance of the tube was going down. Efficiency, the output of the triode was going down. This was because of inter-electrode capacitance. As the tube was having larger size, then it was occupying a lot of space in the PCB, or you can say in the module of a particular equipment. So the overall size of the equipment was large. Then we can come to this high power consumption. As the size of this one was very high and it was having heating element here, filament was to be heated up first. Before making this triode operational, the filament was to be given supply, then it was heating the cathode, so it was taking some time to come for the ready condition. So, and because of the more gap between the cathode and anode, and more power handling of this one, because if you are using this triode on the frequencies, high frequency, plus if you are going to amplify the signal up to the very high power level, it means if this transistor, you can say this transistor is being used in the output stages of the transmitter, where you require the very high level of power, then certainly the power consumption, because of these electrodes having large sizes, the power consumption of tube was very high because its efficiency was very poor. So these were the drawbacks basically for the triode valve, and to overcome all these drawbacks only, or to reduce up to some extent, the transistor, that is your semiconductor device, has been designed. Now transistor is your semiconductor device. So semiconductor, first we have to design a semiconductor material. Semiconductor materials means first we are going for the P-type of material, and P-type of material is formed when you are doping the silicon with some trivalent type of material. So here the P-type material will be formed because the electrons from the outermost, or the valency electrons from the silicon, are getting transferred to this one. So the entire material becomes the P-type. Similarly, we are going to form the N-type of material. N-type you will get when you are doping the silicon with the pentavalent material. So this will give you the P-type and N-type materials. Now we will see that by joining the P-type and N-type material, we are able to form, or we are able to form some structure which will be working like the transistor. Now let us see. If you take here the combinations of the two materials, in this sequence, here if you are having N type, then P type, then N type. So N type, P type and N, these two materials are joined in this fashion. Then one structure is formed here. Now structure will be known like this. This region, first region, N type region, this will be known as emitter. The second region here will be known as base, and this region is known as collector. Now you see the region emitter to base region, this region. The first region is having your N type material. So N type is formed from here by having the doping of silicon with the pentavalent. Then N type material will be formed. It means this N type material is rich in the electrons. It is having electrons as the majority carriers. Similarly, now P type material is rich in the holes. We call them as holes. Holes are nothing but these are the absence, you can say absence of the electrons are known as holes. There is a vacancy for the electrons here. Then similarly, now N type again, collector is formed with N type, so again you will be having the majority carriers as the electrons. Here electrons are the majority carriers. So if you are joining the two materials in this fashion, now let us see the doping part. What is the doping level of all these three regions? Here your emitter, this emitter region is highly doped region. And your base region is your lightly, base region is lightly doped region, and collector region is your moderately doped region. So as the emitter is highly doped region, here the majority carriers are electron and they are available in large number. Excess electrons we are having here, and here you are having the holes as the majority carriers, and in the collector region, as this is moderately doped, so you have few electrons available here. So this will be the structure of this one. Now by joining these two materials, P type and N type, in this fashion, when you are joining, first the two junctions or two depletion layers are formed. These layers will be like this. Or we can see, use and draw only the layer, depletion layer part of this one. So from the base region, as this is positively charged region, or you can say the holes are as the majority carriers here. So on joining these two materials, when you are forming the layers of this one, then what is happening? The positive charge or the holes are entering into the emitter region, and they are available here as positive charge around the junction. Similarly, electrons are entering the base region and they are available here in the form of negatively charged electrons. So this sort of layer will be formed, one side the positive and other side the negative. So we call this one as, and automatically without giving any biasing to this one, this layer will be formed, and this layer is known as depletion layer. Similarly, at this collector to base junction also, it will be formed from collector side, the negative electrons will be coming this side and holes will be entering this side. So here again you are having another depletion layer. This is also the depletion layer. So likewise, you have two depletion layers at two junctions. We are having two junctions. So one depletion layer is available at the emitter to base junction, and other one is at base to collector junction. Now we will come to the biasing parts of this one. Before biasing, first let us understand the size wise. What is the size of these regions? So emitter is having a normal size here. Whatever size it is having, the base region is having narrow, it is smaller size, or you can say this is the narrow size than the emitter size. So this one is your narrow region, and then collector is the largest region. Its size is larger because collector is going to handle the maximum current. The total current which is coming from emitter will be flowing through the collector, and emitter and collector current, we will see this later on. Emitter and collector current are approximately equal, so that is why and plus your saturation current is also available in this. So this region is going to handle the maximum current. That is why the area of this collector region has been made larger in comparison to the emitter. So the size wise, this is your larger size, collector region is larger size, and number 2 is your emitter region, and less than this is your base region. They are the size wise distribution of the areas. Now you see the biasing part of this one. First we have formed these regions, we have designed by joining those two materials. Then let us see how we are doing the biasing of the transistors. So here we have formed the regions as already discussed: emitter, base, collector. If I have taken these regions as N, P and N, then we have certain methods of biasing the transistor. So let us see in what ways we can bias the transistor. First, the emitter is to be connected with negative. If you connect the emitter like this, then your base will be connected with the positive supply, and then again negative and positive. If your NPN transistor, it means you have number of electrons available here, number of holes, then again number of electrons available here. If this type of supply is connected to this one, means negative is connected to the emitter, here positive is connected to the collector, and the base is connected to the slightly positive power supply with respect to the emitter. This is to be done. Now this type of biasing if you are applying to this one, then let us see what happens. The negative of electrode here, from here, the negative electrons, your electrons are coming from the negative terminal, and they will force the electrons from the emitter because of the repulsive force here. The electrons will try to move towards the base region, and they will enter the base region here. And only the potential barrier because of depletion layer available here. This is your 0.7 volt is the potential barrier. Same way it is 0.7 at this junction also. So when your applied voltage is greater than 0.7 volt, that time your electrons from emitter are pushed towards the base, and they will try to enter the base region. As the base is given with the slight positive power supply with respect to the emitter, here you can see in comparison to the emitter, the base will be always given slightly positive supply. So here what is happening, because of positive supply, these electrons are being accelerated. They will be attracted, they will experience the force of attraction in this region. So they are slightly accelerated, and some of the holes will be falling into the, some of the electrons will be falling into the holes, and they will disappear. The recombination process will take place, and then as a result of that you will be having the base current flowing like this in this direction. Now the remaining electrons will be entering the collector region. Now as the collector region, you can see from here, the collector region is applied with the positive power supply, and this positive power supply is greater than the positive power supply at the base. That is why the electrons here in this region will experience the force of attraction from this side, and the electrons are attracted towards the collector. We call this one as collector. So all the electrons which are coming from emitter will be attracted because of the positive charge, because of the attraction, and they will be moving like this to the positive terminal of the battery. So this will be the flow of current. If you take the electronic current of flow, then the electrons are flowing like this from negative to emitter, then entering here, then reaching the collector. They are being then collected by the positive terminal, and this will be the flow of the current. So this biasing is there. In this biasing, the electrons are moving from emitter to collector under the control of base. So this type of biasing and functioning of the transistor is known as active. It means, why we call this one active? Because transistor is functioning in this fashion with this biasing. Here what we call that emitter to base junction is here forward biased. It is forward biased because negative is connected to negative. So we can understand this one as if one diode is connected here from emitter to base. The analogous to this one we can understand in a simpler method. If this supply is connected, this is the part of emitter to base region only. So you can understand now if this type of supply is given, because this region, cathode of this one is corresponding to the emitter and base is corresponding to the anode of the diode. So if this type of supply is connected, then here diode is said to be in the forward bias condition. So here we can say now, with this condition of biasing, that emitter to base region is forward bias. Now here you see, here the polarity is different. Here it is negative region, but here the positive terminal is connected to this one. So again we can represent this region with the help of another diode, and the supply as connected is like this, plus and minus. Now you can see here, this diode is supplied with the positive supply at the cathode and negative at the anode. So this region is reverse biased. So we can say this diode is reverse biased, and this diode is forward biased.